Okay, it should be good. Okay, yeah, it's been a lot of time since we were doing the lectures. We were having midterm, and we have another break from the hurricane. And hope everyone's okay. And now let's back to more about quantum circuits. Okay. And so the plan right now is we'll finish this part about constructing control unitary, and then we'll start talking about actual quantum algorithms. We'll talk about those oracle algorithms. But today I want to finish this circuit construction. Okay. And yeah, so the title is Quantum Circuit World Universality, but unfortunately we don't have time to talk about the full universality. So I guess about universality we'll just leave with this slide, and you will know that a lot of time I guess we will know that C naught, HEDMA, and T gate together is a universal quantum gate set. You can construct any unitary from this gate set, and we will construct something small from them, but we will not do everything. Okay. I guess we don't really construct something. We construct some of the gates from this, and we also construct some of the gates from this. Okay. But anyway, quantum universality, you will know this is the universal gate set, and we try to construct some quantum gates from simpler quantum gates. Okay. And to start with, this is a bit of a review from last time. Okay. So to start with, we define mode notation. Okay. So we define this operator function. Okay. Operator function for diagonalizable matrices. So basically, we want to do function on those poly xyz. Okay. And anyway, so given any diagonalizable matrices, we define a function on matrices. Okay, like this. So if your matrix is diagonalizable with those eigenvalue lambda and eigenstate psi lambda, then we just define a function on the matrix as you put a function on the eigenvalue. Okay, so you have some function f of a, then some function f of x from complex number to complex number. Then the function applied on your matrix is just your matrix with the same eigenvectors, but with the eigenvalue getting applied by the function. So for example, if your matrix is Z matrix, and we know it has the eigenvalue 1 with the eigenvector ket 0, and the eigenvalue -1 with the eigenvector ket 1, and then we can think about apply different function on it. Say we can apply the linear function. F of x is just theta times x, and then this does what you expected. So you multiply the variable by some values theta. So you basically want to multiply your matrix by values theta, and indeed it's just this matrix multiplied by values theta. So it's theta times this 1 minus 1. And let's check out with our definition. We say we change the eigenvalue to f of the eigenvalue. So eigenvalue 1 becomes theta times 1, so it becomes theta. And the eigenvalue -1 become eigenvalue theta times -1 become minus theta. And so this is the simplest linear function, and then we have a more complicated function. So we can take f of x as an exponentiating function. So f of x equal to e to the theta x, where theta is some parameter you set, and some fixed parameter. And then you see that then f of x become e to the theta x. Then if x equal to 1, it's become e to the theta. So this 1 become e to the theta. And if x equal to the -1, it's become e to the minus theta. So this become e to the minus theta. And yeah, so now we define the exponentiating of this matrix Z equal to 1 minus 1. Okay. Exponentiating with some parameter theta e to the theta x Z. We say it's e to the theta e to the minus theta. And here we have more check that saying this definition makes sense. So for example, if your f of x equal to x squared, then you can check that this definition give you the f of a will actually equal to just the matrix A squared, just A multiplied by itself. And more generally, if your f of x is some polynomial, then f of a is the polynomial of your matrix A. Okay, and but what really we this is a bit be the overkill. What we really want is we want to define those three operators. So we want to define this r sub x theta operator, r sub y theta operator, and sub z theta operator. And they are defined as, okay, so I should really draw the defined sign here. Okay, so they are defined by e to the minus I e to the minus I theta over 2 times your matrix X, and for Y is e to the minus I theta over 2 times your matrix Y, and Z is e to the minus I theta over 2 times your matrix over times your matrix Z. Okay, so you have those three matrices, and then we can do the and then you can do the definition we just have on the previous page, and you can write down the matrix as these three matrices, and then you can do a little more to to memorize this thing. Is you realize this excuse me, this operator function definition is very nice. It respects this Taylor expansion. So in particular, because it respects the Taylor expansion, and also because xyz squared to identity, you see that this exponentiation also respects the Euler relationship. So you can expand this out with the Euler relationship. So you by the Euler relation, you have that e to the I theta equal to cosine theta plus I sin theta. This is for some real value. So for some real value theta. And you find out that this works when your theta is actually this e to the minus I theta e to the minus I theta over 2 times your matrix X. Okay, and so you also have a cosine theta component, but now this is a matrix function, so cosine theta component multiply with identity. Then the I sin theta component will multiply by your polymatrix here, polymatrix X, and then polymatrix Y, polymatrix Z. Okay, and so this is we define rotation operator Rx theta, Ry theta, and Rz theta. Okay, and now we have a little more detailed explanation. Okay, and what we call is rotation operator because they are actually related to rotations. Okay. So these Rx, Ry, Rz are actually like a rotation on block sphere around the x-axis, y-axis, and the z-axis, and with angle theta. Okay, and that's why it has a weird, has this weird constant here. So this, you have this minus sign and over 2 here. You might think if you want to just exponentiating of your x, y, z, then why don't you just have e to I theta x, e to I theta y, e to I theta z? And this is because you want to have those three operators being exactly correspond to the rotation on block sphere. Okay, so this is something copied from quantum mechanics 1. So remember, block sphere is like this thing. It says that any one qubit state can be represented as some point on the box sphere, and we were saying that the xyz axis are kind of related to sigma x, sigma y, sigma z, and now we see this in more detail. And for example, this Rx theta will be a rotation on this x-axis, and that means, for example, if we do so for example, if we do Rx and angle being pi, so Rx angle pi, this will be you rotate the whole sphere around x-axis with angle pi, and in particular that will rotate the north pole to the south pole. So we know Rx pi of 0 should equal to 1. And let's check this out. Does this make sense? So Rx pi by the thing we wrote here. So Rx pi equal to cosine pi over 2 times identity minus I sine pi over 2 times x, and okay, does this work out? And yeah, and cosine pi over 2 equal to 0, and sine pi over 2 equal to 1, and so this is equal to minus identity times x, okay, minus I times x. And yeah, so you see that here we have something extra, we have extra phase here, but if we don't care about global phase, then then Rx pi is basically doing the x gate, and so you will rotate 0 to the 0 state to 1 state, but I guess you get a minus I sign here, okay, if you are careful about your global phase, okay, and yeah, and you can check yourself that, or you can check in this exercise photo 7 of the textbook, that Rx, Ry, Rz are actually rotate around x-axis, y-axis, and the x-axis respectively, and with the angle theta being correct. And I guess we can check very quickly. So say you rotate around angle pi over 2, then you should go back to identity. Okay, so if angle theta equal to pi, sorry, not pi over 2. If theta equal to 2 pi, it should be you rotate the whole circle, and it should become identity. And you see that something funny happened. Okay, so when theta over 2 pi, then you have cosine pi, and so that's minus 1 identity, and sine pi. So you have cosine pi and sine pi. So sine pi is 0, and cosine pi is actually minus 1. So so theta equal to 2 pi, then your rotation theta will equal to actually minus identity. Okay, and yeah, and this phase is something it's called Berry phase in physics, and so that's something we don't cover, but this is actually something extra physically, that is sometimes you rotate your system, you will go back to you rotate your system by 2 pi. Okay, so this phase is actually something correspond to what happens if you physically rotate your qubit. So if your qubit is a spin, and sometimes you rotate your qubit by 2 pi, and so you think the state will go back to the same thing, but you will accumulate this weird phase. Okay, and yeah, but that's a bit too much physics, and for now we just think this is you will accumulate some global phase. And so that's a get from the digression. So now we know that the Rx, Ry, Rz are rotations around black sphere. Then we immediately see that so if you have two rotation around the same angle, then you will just be two rotation around same axis. So for example, you rotate around x-axis by angle alpha, then you rotate I guess this is the other way. So you rotate x-axis by angle beta, then you rotate the x-axis by angle alpha, then that should be same as you rotate around x-axis by angle beta plus alpha. Okay, and yeah, so from the being rotation, you see this is true, and more generally you can check this, and more generally you can just I guess not more generally, but if you want to do this more rigorously, you can just also check the expression here, and you see that the exponentials will will add together, and this is true. Okay, and this is true about the rotation operators, and we'll use this for later part of the derivation. Okay, and so that's a bit of a review about the rotation matrices, rotation operators. Any questions? So these Rx theta, Ry theta, Rz theta, they are rotation of black sphere around XYZ axis. Okay, if not, and then we'll start doing start doing what we want to do today, and that is basically we want to construct any basically the goal today is actually right here. We want to construct any controlled unitary from C naught single cubic gate. Okay, this is kind of our goal. And in particular, single cubic gate, we also like, anyway, yeah. And so to do that, first we do is we decompose single cubic gate into the rotations we just say. Okay, so we say any single cubic gate, single cubic unitary U, and we want to decompose them into rotations. Okay, and this has intuitive derivation. Okay, so intuition is that we say any unitary operator on a sphere is basically a rotation of the sphere around some axis. Okay, and then you can just do by I guess this is geometry. So you can do by geometry. You will know that any way to rotate the sphere can be decomposed into rotation around the axis and the rotation around y-axis, then the rotation around the axis. And this is unitary, so there is possibly there is some global phase, so there is extra global phase E2I alpha here. Okay, so intuitively this says that if you want to rotate your sphere in any way, then then you can do some rotation around y-axis, then rotation around the axis, then rotation around y-axis. Okay, and yeah, but we can also do more detailed proof, and here is basically the derivation here says that is quite detailed, so we don't go into detail. Basically, you try to parameterize unitary as A, B, C, D, and you try to count all the degree of freedom, and then find out that indeed this E to I alpha, RZ, RY, RZ, RZ beta, RY gamma, RZ delta can parameterize any unitary A, B, C, D. Okay. So you basically count all possibility of A, B, C, D, while U is still a unitary, and you find out that indeed this RZ, RY, RZ covers all possibility, and you multiply all RZ, RY, RZ, and you see they look like this. So you have all the possible tuning of the phase and the amplitude here. Okay, so we kind of gloss over this proof, and then we go to next one. Okay, so we decompose single cubic unitary like this, and then we decompose single cubic unitary even more. Okay, and now we want to decompose into a bit higher sequence. Okay, so we want to decompose any single cubic unitary into this weird sequence E to the I alpha, and three matrix A, B, C, and two poly X. Okay, so we want A times poly X times B times poly X times C. Okay, so yeah. So we want to decompose any single cubic unitary into this weird sequence, and this sequence also need to satisfy that A times B times C equal to identity. We'll see later that this is how you construct a control unitary. Okay, and but anyway, let's start proving this, and we start with the ZY decomposition we just have. So we know any unitary U can be decomposed into this E to the I alpha global phase, and RZ beta, RY gamma, and RZ delta. And we are just going to construct our ABC from those beta, gamma, delta. And here we have the exact construction. So A is RZ beta, RY. So I guess you can just read here that this ABC are some rotation around Y, Z and Y, and with angle related to beta, gamma, delta. Okay, and so basically we have two things to check. Okay, and so we need to check well, just those two things here. We need to check ABC multiply integral equal identity, and AX this E to I alpha AX BX C equal to your unitary, and then basically we need to check that. So two things to check. First one is ABC equal to identity, and then the second one is check U equal to this thing. But we already have this U equal to this decomposition of beta, gamma, delta here. So basically, we want to check this part equal to this part. So we want to check ABC equal to identity and AX, BXC equal to the beta, Y gamma, and the delta. Okay. And yeah, so now let's do check a little slower. So first one, ABC equal identity is easier. So you just multiply ABC. Okay, so let's do this. So ABC equal to the beta Y gamma over 2. Then B you have Y minus gamma over 2. And RD minus delta plus beta over 2. Then finally C is RD delta minus beta over 2. So you see that we set up things nicely because now we know these RD, RY are rotations. So in particular, okay, my writing is kind of bad. So these so you see we have Ry gamma over 2 and Ry minus gamma over 2 here. And so they will cancel out because you rotate Ry by angle gamma over 2, then you rotate angle minus gamma over 2, so cancel each other. And so now you just left with 3 RZ term. And then the angle here we should also cancel out. So the RZ term, you are left with beta and minus delta plus beta over 2. And then plus delta minus beta over 2. Okay. And so the delta cancel each other here, and you have a beta minus beta over 2 minus beta over 2. So beta cancel each other, so this is RZ of 0, and this is equal to identity. Okay, and yeah, so you see that we set up things nicely, such that A times B times C, the rotations cancel each other, and you just have the rotation of angle 0, and this is identity. Okay, and then the next one is we need to prove this AX, BXC equal to RZ beta, RY gamma, and RZ delta. And this is actually pretty easy because you just need to know what XBX do, okay? And what XBX do is you will realize this is X is sandwiching some function of sigma Y and some function of sigma Z. And there is a very easy relation you can have for this X sandwiching function of Y and X function of Z. It's just that you have an operator function of Y and they sandwich it by 2x, and they will just be the same function with minus 1. And similarly, you have a function of Z is sandwiched by some x, then it will be some function of minus Z. Okay, and I think this should be true for everything, but for easiness of proof, let's assume f has some Taylor expansion. Okay, so x is some polynomial, summation n, a, and xn. And the proof is that you write your f as a polynomial. So your f of y is the summation of your a and y to the n. And then I guess I should write this longer. Okay. And so you have so because you have x squared equal identity and xy equal minus y, so we have this x y y y. You think about this x y y y x term, and this equal to x. So you can insert 2x squared inside between every y. Okay, so you can insert x squared between every y because x squared equal identity. So you have x y x, x y x, da 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 to x y x, and this thing then. Yeah, because the poly anti-commute, or you just can check this proof falsely, you know that xyx equal to minus y. Okay. And so xy is equal to minus y, so this is just equal to minus y times minus y, times minus y. Okay, so you have ny here, then just then so you have ny here, and you symmetry in x, you see that you just have n minus y. Yeah. And yeah, so and this thing works linearly. So for any n, is become y to n become minus y to the n. So in the end, you have a summation an minus y to the n, and that is just f of minus y. Okay, and so similarly, you have f of z symmetry by x become f of minus z. And now finally, we can go back to what is xbx. Okay, so we now think about this xbx part. Okay, we go to this xbx part, and we see that so we need to remember b. B is this ry minus gamma over 2 rz minus delta plus beta over 2. Okay, and the symmetry by x. So symmetry by x, ry minus gamma over 2 rz minus beta plus delta over 2, and just like what we did before, we can insert the identity here and the identity equal to 2x. Okay, so we have 2x between this ry and rz, and now we have two components. We have a function of y symmetry by x and a function of z symmetry by x, and we know that it just become function of minus y and function of minus z. Okay, and I guess we jump ahead a little bit, but you can also show that by just the definition of ry theta and z theta. So you can show that r theta of I guess not r theta, sorry. So you can show that if you have kind of r minus y, you have r minus y of theta will equal to r of y minus theta. Okay, you can check by the definition of ry, and similarly for rz. Okay, and so what the symmetry do is you will get a minus sign on your theta, so this minus gamma over 2 become plus gamma over 2, and this minus delta plus beta over 2 become plus delta plus beta over 2. And yeah, so finally you can put everything together, and now because you have this flip sign here, your ABC multiply ABC sequence become different thing. So ABC become so A is this part, so ABC become this thing. So A is this, and B now XBX become the middle part, and C is this, still this thing. And once again, we group together the rotation around the angle. So we have RZ beta here, and now we have Ry of 2 Ry of gamma over 2, and the 8 scalar, so you just have Ry gamma here, and finally you have RZ of delta plus beta and delta minus beta, and so that's RZ delta. Okay, so we see that we set up everything correctly, and we have that e to I alpha xbx a xbxc is indeed equal to our decomposition e to I alpha rz beta ry gamma and rz delta, and this is equal to our unitary u. Okay. Any question? Okay, so this is still set up, and so now from the zy decomposition, we have this, I guess, ABC decomposition of single bit unitary. And finally, from this single bit ABC decomposition, we can do arbitrary control operator by by single by single cubic unitary and C naught. Okay, and okay. So we have any single cubic unitary u, and we want to control a control version of it. Okay, so we want to do control u, which means that if the first cubic is 0, you do nothing here. First cubic is 1, you want to apply the get u here. and we did and so how we did is we do this decomposition of u equal to e to I alpha ax bx c. Okay, so this is exactly what we want, exactly what we just did. We know we can always decompose u as is e to I alpha ax bx c, and we know these abc are some rotation around y and z axis. But for now, we just think ABC are some single cubic gate. Okay, and yeah, and sorry for typo, ABC not equal to 0, ABC equal to identity. Okay, and okay, and so we have just our circuit here. Okay, so circuit here, and so on the second wire we have ABC, and where B and C in the middle we put a control node here. And then we do this weird phase gate e to the I alpha, 1 and e to the I alpha on the first qubit. And we cannot, oh sorry, more typo, okay. And so we cannot just do the control U, so we need to basically check two things. So we need to check that when first qubit is 0, then the second qubit, then nothing happened. And when the first qubit 1, then you apply U on the second qubit. Okay, and so let's check one by one. So when first qubit is 0, then the CNOT gate does nothing, right? So now we check the 0 case. So when first qubit is 0, then control on 0, the CNOT base does nothing, so you have no CNOT here. And second qubit, you have so this is really a little funny, but this ABC actually act with the order BC, CBA. Okay, so you have C times B times A equal to identity, and so second qubit get acted by identity, so second qubit doesn't get nothing, and the first qubit, well, the CNOT does nothing, and you have this gate, this 1 e to I alpha here, and you have a 0 on this thing, and it will just act on 1. And also nothing happened to the first qubit. Okay, so when first qubit is 0, then nothing happened on first qubit and nothing happened on second qubit. Okay, and so that's the first qubit being 0, and then now we check what if the first qubit is 1. Okay, so first qubit is 1, then the CNOT will become basically a Pi gate on the second qubit. So you have X here, okay? And so what happened on second qubit is you will get CXBXA, okay? And also also this gate will give us actually a global phase, okay? This e to then because you have a 1 here, so we will pick up this e to alpha phase. So we will get this e to alpha phase, and also get this CXBXA on the second qubit. And so if we just push the global phase to the second qubit, then you see that the second qubit gets acted by this unitary e to the alpha AXBXC. Okay. And yeah, so and we know this e to the alpha AXBXC is exactly a unitary we want to apply. Okay, so when first qubit is 0, nothing happens on second qubit. When first qubit is 1, second qubit gets applied by unitary U, and this is so this is by the linearity we know that this is a control unitary we want. Okay, so you have a superposition, then on the first qubit, then you have the superposition of the result. Okay, and so that's I guess the most complicated construction we have today. Okay, and we set up this with two previous lemma, the YZY decomposition of a single qubit unitary, then this ABC decomposition, and then finally we can have this arbitrary control of single qubit control of a single qubit unitary. Any question? If not, okay, then yeah, so this is arbitrary control operator, and then we can now we generalize it a little bit to have control more qubits. We have more control, and so we'll generalize this to I guess later we will still control only single qubit gate, and but we have more controls. Okay, but before that we get some notation. So we have the C2NU. Notation means you control n qubit and apply a unitary on some number of qubits. Okay, so you control n qubit here. So here I have n equal to 4. Okay, and this just means a gate that control n qubit and apply unitary on some other qubits. Okay, so for example, so the C2N, if your control unitary is controlled qubit is in computational basis state x1, x2 to xn, and then you and the target qubits are in this state psi, and you apply your C2N unitary, then will be the control unitary, the control state doesn't change. But the target state get multiplied by the unitary if only if this x1 times x2 times xn equal to 1. So this notation here is a little bit of ambiguous. This means x1 times x2 times times xn. So they multiplying together, and x1, x2 to xn are number from 0 to 1. So this is equal to 1 if only if they are all 1. Okay, whereas it's just 1 0, this is 0, and u2 0 is identity. Okay, so this is some notation, and but let's get back. So we have this 1-bit controlled unitary, and now we take baby step. We'll go to 2-bit controlled unitary. And then from now on, we kind of hand waving, and we just give proof. We just give construction here, and we don't go to details of the proof. Okay, and we just can that indeed this any 2-bit control unitary can be controlled from CNAT and single qubit unitary for any single qubit U by just this circuit. Okay, so you have this 2 control unitary, and it can be applied by, it can be constructed by this circuit where this is CNAT here, and we have 3 weird things. So we have control V dagger, and control V here. So V is basically the square root of U. It's easy to prove that this unitary always exists. So you have V such that V squared equal to U. V is also a single qubit unitary. And so instead of control U, you have control V here. Okay. And yeah, so you have a control V here, and so control V dagger, and control V. Yeah. Yeah, and I think the idea here is that if those are not both 1, then things will get cancelled out. So let's see. Let's try. This is dangerous. Okay. So let's check. So there are 4 possibilities here, and let's do an easier one. So maybe the first qubit is 0, and the second qubit is 1. Okay. So first qubit is 0, so all those control doesn't work. Okay, so we saw control on 0, they don't do anything. And it's 1 here, and so second qubit will apply a V on the third qubit, then a V dagger on the third qubit, and V dagger will cancel out, so nothing actually apply on the third qubit. And I'll check out with when it's 0 1 here, then nothing happen. And you can check all other 3 cases, and they do exactly what you expected. Only when you have 1 1 here, you apply V squared equal to U here. Okay, and also we know that we can apply control V here, because we already said that any control unitary we can apply with CNAT and single qubit unitaries. Okay, so with CNAT and single qubit unitaries, we can also do this double control U. Okay, and in particular, if you think this U is X, then we go back to a very famous gate that is a Toffoli gate. So it's C squared X. Okay, and so with this construction you can do Toffoli, but this is a bit of digression. People also like to decompose Toffoli in this thing. because we also think this HESMA T and CNAT is a universal gate set, and so people would like to decompose tupley into HESMA T and CNAT, and that will be this gate. Okay. This looks a bit more complicated, but you only have CNAT, HESMA, and T. And I guess here is S, but S equal to T squared. Okay, so the tupley gate is pretty cool. And it's pretty cool also because from tupley gate we can we can go to our lace construction. Okay, so this is the lace control unitary we want to do today. And basically finishing of this part. That is, we want the control unitary on arbitrary number of controls, and but target qubit is still only 1 qubit. If you want to see target qubit having more qubits, and you need to read Newton Tron. But I think this is a pretty cool construction. Okay, so we can implement C to the NU with NU and NU and NEN by this circuit. And we actually need some ancilla qubits. Okay, so this construction is a little wasteful, but it's conceptually simple. So here this is a control unitary. So you have n control qubits here. So you control on those qubits, and as we say, you have 1 target qubit here. And we also have some ancilla here. So you need to have some extra work qubit here. And so what you do is you will do a whole bunch of tupley. Okay. And so you have a C1, C2, control on C1, K2, and a tupley on the first qubit. And control on C3 and the first qubit, target on the second qubit. And so we can think about what happened here. And that is, you have a control on C1, C2 here, and so now this point will become C1 times C2. So this qubit got flipped only if both C1 and C2 are equal to 1, right? Because that's just what tupley do. So when both C1 and C2 equal to 1, it becomes 1. And similarly, here you see that this qubit becomes C1, C2, C3, because this becomes C1, C2, C3. Sorry, let me write this better. This becomes C1, C2, C3 because it's 1 if only if C3 is 1 and this point is 1. Okay? And this point is C1, C2, and this is C3, so this is C1, C2, C3. Okay? And so all the way down, so you can see the same logic. So this is 1 if only if this is 1 and this is 1, and that means this is 1 if only if all C1, C2, C3 equal to 1. And similarly, this point is 1 if only if C1, C2, C3 equal to 1, and C4 also equal to 1. And this point is 1 if only if all 5 qubits here are 1. Okay? And so this is 1 if only if C1 to C5 all equal to 1. Okay? And then you apply your control unitary. So now this is just a single bit controlled single bit unitary. Okay? And this can be done by our ABCD composition. Okay? And so you see that you apply this control unitary if only if all those five bits here are 1. Okay? And so if any of them is 0, then you do nothing here. Okay, and if they are all 1, you apply your unitary. And then there is something a bit confusing here, but you actually need to clean up all your work qubits. This is something you can check yourself, that if you don't clean up your work qubits, then actually you will lose coherence in your control qubit, and then you are not applying this unitary anymore. Actually, you apply what's called a quantum channel, because your control qubit here will, I guess the control qubit and your target qubit together will no longer be a pure state. Okay, and so you need to do clean up here. So basically, you need to uncompute all the things you write down from control unitary here, and turn your work qubit back to all 0 state. And in that way, you will not decode here your control qubit and a target qubit, and it will apply your control unitary. Okay, and yeah. So control qubit, and you kind of do the calculation in the world qubit. You use those Tabli gates to do kind of multiplication between those C1, C2 to C5, and based on they are O1, you apply your target qubit, then you compute your world qubit, and that will be your multi-qubit control operator. Okay. And you can probably feel a little bit that this is not the most efficient construction, and indeed there have been research done how to do this control unitary with less world qubit or less world qubit or less circuit depth, etc. Okay, so a lot of things have been done to optimize this construction here. Okay. And I think that's about time. We have 1 minute left. So if there is no question, that will be end of class today. And the next time, I guess we can flash a little bit of what's going next. Next time we'll start talking about quantum oracles, and we'll talk about oracle algorithms, where we can prove quantum speed up over classical algorithms. Okay, so we use quantum oracle in quantum algorithm, and we find out that they have provable speed up over classical oracle algorithms. Okay, yeah, that will be next time. So see you on Thursday. Okay.